let's move on to tree diagrams. If there are multiple events, this can be very useful, but really only if there's a limited number of outcomes. Each stage of the tree represents one event. So in this example, a coin is tossed 3 times. So we want to draw a tree diagram. We start with a node, and there are 2 possibilities, either heads or tails. That's the first roll. Now, each of those branches then has 2 more possibilities for the second roll. And then each of those branches has 2 more possibilities for the third roll. And if it's a fair coin, there is exactly half a chance or 50% chance of any one of those tosses. So that's our complete tree diagram. The probability of getting 3 heads in a row, and there is only 1 branch that gives us that outcome out of a possible 8. The answer is simply 1 over 8. Another way of working it out is to write it like this, because for multiple events we multiply the probabilities together. So here we just have a half times a half times a half, which equals 1 over 8. To get the probability of exactly 2 tails, we just look through our tree and you'll see there that there's 3 roll orders that will give us that outcome. So the probability is 3 out of 8. Let's go one step further. Some tree diagrams can become quite large, which makes them difficult to draw. So instead of a basic tree diagram, we draw a probability tree diagram, which does not list all events. So here's another coin and die experiment. And we could draw our tree diagram like the one on the left, where we list all the outcomes, or we can do it more simply, shown on the right. We can't really simplify the tossing of the coin. There's exactly half a chance of getting a head or half a chance of getting a tail. But if we're only interested in finding the probability of getting a 6 on the die, then we can use the idea of complementary events. So we're either rolling a 6, which has a probability of 1/6, or not getting a 6, and there's 5 possibilities out of 6, or 5/6. So this is much simpler, and the answer to this shown underneath, the probability of a head and a 6 is just a half times 1/6, which is 1/12. There's a very important feature here about tree diagrams we should note before moving on. The sum of the probabilities for each set of branches is exactly 1, and this is always true. So let's have a look at a couple. A half plus a half is 1. There's 2 possibilities when we toss a coin. The total of the probabilities must add up to 1. And over on the other side, the idea of the complementary event, we have 1/6 plus 5/6. So when you're setting up these diagrams, always make sure that your probabilities add up to exactly 1 for each set of branches. Here's another interesting example. We have 25 playing cards. We still have 4 suits, but there are an unequal number of cards in each suit. So what will our tree diagram look like? So we start off the same way, we list our suits, but because there's only 10 cards that are hearts, there's a 10 over 25 chance of drawing a heart, and the other probabilities are worked out the same way. If you add those 4 numbers together, they must add up to 25 over 25, or 1. If we wanted to find the probability of drawing a red card, for example, there are only 2 red suits, the hearts and the diamonds. So we add those probabilities together, which is 15 over 25, and that reduces to 3/5. Another example that I find quite interesting. It is found from experience that 70% of the public enter a cricket ground through Gate A and 30% through Gate B. It's also usual to expect 20% of the patrons to be pensioners. So the question is, what will our probability tree diagram look like? There are two gates, and there are two possibilities for people entering those gates. They're either pensioners or they're not pensioners. So let's go ahead and label everything. There's a 70% chance of someone entering through Gate A, and I've changed the percentages to decimals because they're easier to work with. And for the age, we have non-pensioners and pensioners with the probabilities shown. So what is the probability that a randomly selected person is a pensioner who enters through Gate B? Well, the probability, we remember that these are independent events, so we multiply the probabilities together, and it's 30% times 20%, or 0.3 times 0.2, which is just 0.6. One last example, and I always find these fun for some reason. We have a bag with red and blue marbles. We're drawing two marbles from the bag. In A, find the probability that the first is red and the second is blue if the first marble is replaced. So once again, we draw a tree diagram. There's two possibilities, red or blue, but the probability of each is not the same. There's 4 chances in 10 of drawing a red and 6 chances in 10 of drawing a blue. So we replace the marble and draw again. So there are 2 possibilities for each branch. And again, noting that we are replacing the marble, the probabilities will be the same as for the first draw. 4 in 10 chance of getting a red and a 6 in 10 chance of getting a blue. So the probability of a red followed by a blue, have a close look at the tree diagram and you'll see that there's only one branch that gives us that outcome. So we multiply the probabilities together and that reduces to 6 over 25. In B, we change the scenario. We start the same way for the first draw, but now we're replacing the marble. There's still 2 possibilities, but now the probabilities are different because instead of 10 marbles in the bag, there's only 9. So if we drew a red to begin with, we no longer have 4 left, there's only 3 left, and there's only 9 marbles in total. So the probability of drawing a red, if we have already drawn a red and have not replaced it, it's only 3 over 9. The probability of a blue, there's still 6 marbles, but remember there are only 9 marbles in total left in the bag. Now remember, those have to add up to 1. 3 ninths plus 6 ninths equals 1. For the other branch, if we draw blue, the probability of drawing a red after that, if we don't replace the blue, once again there are 9 marbles left instead of 10, but we still have our 4 original red marbles. For the blue, we've already drawn 1, so there's 5 left instead of 6, and there are 9 left instead of 10. So to work out the probability of red followed by blue without replacement is 4/10 times 6 over 9, which is 24 over 90, or 4 over 15. And you should realize here that there's a slightly greater chance of drawing a red followed by blue in the second case if we don't replace the red. That's because there are more blue relative to the number of reds in the bag than when we started. Alright, so I hope you found that review helpful. We have several different ways of solving these problems, and it's good practice to revise each of those methods and also realize that different questions are better suited to some approaches more than others.